September 3, 1942. Luftwaffe Test Facility, Rechlin, Brandenburg. Autumn fog rolls across the airfield as heavily guarded convoy arrives before dawn. Inside the secure hangar complex, German aviation engineers have assembled, summoned without explanation, authorized for intelligence matter of extraordinary sensitivity. Oberingenieur Hermann Dietrich stands at attention as military police unlock the transport bay. What emerges defies immediate comprehension. Avro Lancaster bomber, 4 Rolls-Royce Merlin engines, massive wingspan stretching 102 feet across the hangar floor. This is not wreckage salvaged from crash site. This is largely intact aircraft, forced down over occupied Netherlands with minimal damage. Crew captured, airframe recovered before British could destroy it through bombing. Dietrich approaches slowly, his engineer's mind struggling to process the implications. This machine represents the opponent he believed technologically inferior, industrially primitive, strategically desperate. Its dimensions mock the He-111, the Ju-88, every medium bomber in Luftwaffe inventory. He has designed aircraft for 17 years, worked on Dornier projects, contributed to Heinkel development, believed German heavy bomber programs led the world. Now he confronts aluminum evidence that belief was comfortable fiction. The night war over Germany is becoming catastrophic, and this is the weapon delivering that catastrophe. The examination begins with systematic German thoroughness. 34 engineers, 8 structural specialists, 12 propulsion experts, 7 aerodynamicists, 6 systems analysts. They work continuous shifts, documenting every component, every system, every design decision embedded in this nocturnal leviathan. The specifications accumulate like prosecutorial evidence. Wingspan 102 feet, 20 feet wider than He-111. Maximum takeoff weight 68,000 pounds, nearly double most German bombers. Bomb load capacity, 14,000 pounds standard, 22,000 pounds with modifications, 3 times typical German payload. Range 2,530 miles with standard load. German bombers struggle past 1,500. Operational ceiling 4,500 feet. Altitude providing some protection from flak while remaining below heavy fighter altitude. These numbers violate everything Dietrich understood about strategic bombing economics, everything technical assessments concluded about optimal bomber design, everything intelligence reports claimed about British industrial limitations. The structural design astounds them most. The Lancaster's fuselage is built around massive unobstructed bomb bay, 33 feet long, no internal structures interrupting the space. German bombers carry bombs in multiple small bays, limiting maximum weapon size. The Lancaster can accommodate single 22,000-pound Grand Slam bomb, or single 12,000-pound tall boy, or standard load of smaller weapons. This flexibility reflects different design philosophy. British optimized for payload versatility, accepting structural complexity. Germans optimized for manufacturing simplicity, accepting payload constraints. Hauptmann Klaus Werner, chief structural engineer, spends 96 hours studying the airframe. He photographs load-bearing members, traces stress paths, analyzes joint designs, measures skin thickness variations. The structure incorporates geodetic construction principles borrowed from Vickers Wellington, but simplified for faster production. Each component precisely sized for its stress load, nothing overbuilt, nothing underbuilt. The engineering reveals sophisticated understanding of structural optimization that German designs often miss through conservative over-engineering. But something else captures Werner's attention: battle damage evidence on the captured aircraft. Multiple flak holes patched by British ground crews before the forced landing. Inspection reveals damage pattern, holes through non-structural areas, carefully routed systems avoiding single-point failures, redundant control runs, fuel tanks with self-sealing capability. The Lancaster absorbs punishment that would down German bombers. This is not accident. This is designed survivability. Engineer Franz Becker calculates structural weight fractions with growing amazement. The Lancaster achieves 22% structural weight fraction, remarkably low for aircraft this size. German bombers average 27 to 30%. The British somehow built lighter, stronger, more damage-tolerant structure than German heavy engineering tradition produced. They achieved through intelligent design what Germans attempted through robust materials: efficiency over robustness, optimization over conservatism, and it worked spectacularly. October 1942. The reverse engineering project receives official designation, Program Löwe, Lion Program. Reichsmarschall Hermann Göring personally demands comprehensive analysis, immediate application of lessons to German bomber development, explanation for how British achieved such capability. Oberingenieur Dietrich knows they face profound challenge. The Lancaster is not incrementally better than German bombers. It represents fundamentally different design philosophy achieving dramatically superior payload range survivability balance. German heavy bomber programs have consistently failed. The He-177 plagued by engine fires, the He-111 too small for strategic bombing, the Do-217 adequate but limited, and Britain mass produces this four-engine giant that raids German cities nightly with impunity. The first assessment cuts through comfortable denial. The Lancaster's structural design cannot be easily replicated in German production. Its construction requires precision manufacturing, skilled labor, complex tooling. More critically, it requires 4 Merlin engines per aircraft. Germany lacks equivalent power plant. The BMW 801 Radial produces adequate power but creates excessive drag. The Jumo 211 liquid-cooled engine is underpowered. The DB603 shows promise but remains in development, plagued by cooling problems and manufacturing difficulties. Engineer Otto Schneider calculates production implications with brutal mathematics. Germany's aluminum supply has tightened severely. Allied bombing of refineries, loss of bauxite sources, increasing demands from fighter production. Building Lancaster-scale bombers would consume aluminum that could produce 3 medium bombers or 6 fighters. The resource allocation question becomes strategic. Concentrate on fewer heavy bombers with greater individual capability, or maintain larger numbers of smaller bombers with limited individual effectiveness. Major Heinrich Baumann, Luftwaffe Strategic Bombing Liaison, presents the operational dilemma to Dietrich with unusual frankness. The night war is destroying our cities. The Lancaster is primary weapon delivering this destruction. We need countermeasures, better night fighters, improved radar, stronger air defenses. But we also need understanding. Why is this bomber so effective? What makes it survive our defenses? Can we build equivalent capability? These questions frame the analysis. Not merely technical curiosity, but operational necessity. Dietrich reviews options with his team through October nights punctuated by RAF bomber streams overhead. They could attempt direct Lancaster replication, maximum capability, impossible with available resources. They could adapt Lancaster principles to German industrial reality, moderate gains, significant challenges. They could focus on improving existing designs, incremental improvements, inadequate results. Every option involves compromises between theoretical excellence and practical constraints. The Lancaster represents what British could build with their industrial methods, operational doctrine, strategic priorities. Germany must achieve effectiveness through different path or accept continued vulnerability to strategic bombing. The psychological impact spreads through Rechlin like creeping paralysis. Engineers who spent careers advancing German aviation now confront captured aircraft, demonstrating British capability far exceeding intelligence assessments. The Lancaster's superiority is not subtle or debatable. It is categorical, measurable, undeniable. This machine carries 3 times the bomb load over longer distance, with better survivability than anything Germany produces. The implications are strategically devastating. Some retreat into technical rationalization. Oberst Gustav Richter insists Lancaster advantages reflect British desperation, that 4-engine bomber is wasteful of resources, that German medium bombers provide better overall effectiveness through greater numbers. He writes memoranda emphasizing Lancaster vulnerabilities: large radar signature, heavy weight reducing maneuverability, complexity limiting production rates, dependence on 4 engines creating maintenance burden. These observations contain partial truth. They avoid acknowledging that nightly Lancaster raids destroy German industrial capacity, kill thousands of civilians, force massive diversion of resources to air defense, undermine civilian morale. The Lancaster is strategically effective regardless of tactical vulnerabilities. Others embrace uncomfortable clarity. Hauptmann Werner begins documenting not what they learned from Lancaster, but why German heavy bomber development consistently failed while British succeeded. His reports read like institutional autopsy. Germany's decision to prioritize tactical air support over strategic bombing in 1930s, building aircraft for battlefield support rather than deep interdiction. The failure to develop adequate heavy bomber engines when peacetime allowed research investment. The emphasis on dive bombing capability that compromised structural design of He-177. The constant requirement changes disrupting development programs. Each insight reveals systematic failures of strategic planning, industrial coordination, doctrinal clarity. Oberengineer Dietrich reads these assessments alone in quarters overlooking the airfield. Through windows, he watches German night fighters scramble against incoming RAF bomber streams. Inadequate numbers, limited effectiveness, desperate response to overwhelming threat. The Lancaster represents Britain's strategic choice made correctly years ago. Invest in heavy bomber force capable of striking enemy homeland. Accept the resource cost. Maintain development focus. Build industrial capacity to sustain production. Germany made opposite choice. Invest in tactical aircraft supporting ground forces. Minimize resource commitment to strategic bombing. Allow development programs to drift. Accept limited industrial capacity for large aircraft. Both choices were rational within their contexts. One proved strategically prescient. The other left Germany vulnerable to exactly the threat now devastating its cities nightly. November 1942. Test flights begin with the captured Lancaster after German crews complete familiarization training. Test pilot Hauptmann Erich Hartmann, experienced in heavy aircraft from transport operations, takes the controls for first evaluation flight. The bomber handles ponderously, but predictably. Controls are heavy but responsive. The four Merlins produce smooth, reliable power. He climbs to 15,000 feet over Baltic, begins performance testing. Maximum speed, 287 miles per hour at altitude. Cruise speed, 216 miles per hour. Rate of climb, 720 feet per minute fully loaded. Service ceiling, 4,500 feet. These figures confirm British specifications. The Lancaster is not fast, not agile, not particularly high-flying, yet it succeeds strategically through different virtues. Hartmann analyzes why during 2-hour test flight. The aircraft is stable bombing platform. Visibility is excellent for crew coordination. Systems are logically arranged. The bomb bay accommodates enormous weapons. And critically, the structure absorbs vibration, reduces crew fatigue, enables long-duration missions. After landing, Hartmann writes assessment with bomber pilot's perspective. The Lancaster is not superior through performance specifications. It is superior through operational effectiveness. This aircraft allows crew to function efficiently during 8-hour missions over hostile territory. The British designed for crew endurance, mission completion, payload delivery, not for speed or altitude. They optimized for strategic bombing reality rather than tactical aircraft theory. We optimized German bombers for tactical performance while neglecting operational sustainability. The Lancaster succeeds because it addresses actual operational requirements comprehensively. This observation illuminates the fundamental design philosophy gap. German bombers emphasized speed and maneuverability, attributes valuable in tactical operations, less critical for night strategic bombing. British emphasized payload capacity, structural durability, crew efficiency, attributes enabling sustained strategic campaign. Neither approach was wrong abstractly, but strategic bombing's actual requirements favored British philosophy. Engineer Becker analyzes combat damage tolerance through structural testing. They deliberately inflict simulated battle damage, removing structural members, cutting control cables, puncturing fuel tanks. The Lancaster remains controllable with surprising levels of damage. Redundant systems, careful routing of critical components, structural load path diversity. The design anticipates battle damage and provides graceful degradation rather than catastrophic failure. German bombers, by contrast, often fail catastrophically from relatively minor damage. Single-engine failure frequently leads to loss of control. Fuel system damage causes fires. Control cable damage renders aircraft unflyable. The design philosophy emphasized efficiency over redundancy, performance over survivability. This works adequately when opposition is light. Against heavy defenses over Germany, it proves fatal. The Lancaster's indestructibility is not accident. It is engineered resilience systematically designed into structure and systems. Behind the technical project, parallel intelligence operation unfolds. The Abwehr assigns special section to investigating how Britain developed such effective heavy bomber. Oberst Alexander Koch leads team analyzing captured documents. interrogating aircrew prisoners, reconstructing organizational infrastructure behind Lancaster's creation. What they discover illuminates systematic British approach to strategic bombing development. The Lancaster emerged from institutional learning and rapid adaptation. Its predecessor, the Manchester, failed due to inadequate twin-engine configuration. Rather than abandoning the design, Avro chief designer Roy Chadwick redesigned for 4 engines, strengthened structure, enlarged bomb bay. The Air Ministry supported this development despite resource constraints because strategic bombing doctrine demanded heavy bomber capability. The Lancaster flew in 1941, entered service rapidly, continuously improved through operational feedback. This represented organizational agility Germany rarely demonstrated, admitting failure, adapting quickly, implementing lessons learned. German heavy bomber development followed opposite trajectory. The He-177 program persisted for years despite fundamental flaws, coupled engines causing fires, dive bombing requirement creating structural problems, constant specification changes disrupting production, resources consumed, years wasted, minimal operational capability achieved. No institutional mechanism existed for admitting program failure and pivoting to alternative approach. Bureaucratic momentum, political commitment, doctrinal rigidity prevented adaptation. Koch's reports document systematic British advantages in bomber development. Air Ministry maintained clear strategic requirements providing design stability. Manufacturers competed for contracts but shared technical data. RAF Bomber Command provided operational feedback directly to designers. Research establishments contributed wind tunnel data, structural analysis, systems optimization. The entire British aviation sector functioned as coordinated system focused on strategic bombing effectiveness. Germany's bomber development suffered from institutional fragmentation. Luftwaffe specifications changed frequently based on tactical experience. Manufacturers guarded proprietary information. Operational feedback rarely reached designers systematically. Research establishments pursued academic interests disconnected from operational needs. No coordinating mechanism aligned these elements toward common objective. The analysis extends to production philosophy. British bomber production emphasized building fewer aircraft to higher quality standards with skilled labor. Each Lancaster received careful assembly, thorough testing, complete equipment installation. Production rate was approximately 300 per month, modest by German standards but adequate for strategic requirements. German production emphasized quantity over quality. More aircraft produced faster with less skilled labor. This philosophy worked for fighters and tactical aircraft. It proved inadequate for complex heavy bombers requiring precision assembly and comprehensive systems integration. Koch's final report concludes, Britain succeeded in heavy bomber development not through superior technology, but through superior process, clear strategic vision, organizational agility, institutional learning, coordinated development. We possess comparable technical capability. We lack comparable organizational effectiveness. The Lancaster's success reflects their system working correctly, not miracle weapon creation. December 1942. The moral weight becomes crushing. Oberengineer Dietrich sits in meetings with Luftwaffe commanders demanding immediate countermeasures, technical solutions, explanations for why German cities burn nightly while British industrial centers remain largely intact. He provides technical analyses while knowing they address symptoms rather than causes. The Lancaster is excellent bomber, but Britain's strategic bombing success reflects more than aircraft capability. It reflects years of doctrinal development, operational experience, industrial commitment that Germany never matched in heavy bomber aviation. The ethical dimension becomes personal when Dietrich visits Hamburg after devastating RAF raid in November. Entire neighborhoods reduced to rubble, thousands dead. Survivors wandering through ruins. He understands intellectually that this is strategic bombing's purpose: destroy enemy industrial capacity, undermine civilian morale, force resource diversion to defense. But witnessing destruction firsthand transforms abstract strategy into human tragedy. The Lancaster is instrument of this destruction. Understanding its technical excellence while seeing its effects creates profound moral dissonance. Hauptmann Werner confronts this differently. He argues forcefully in planning meetings that Germany should abandon heavy bomber development entirely, concentrate all aviation resources on fighters and tactical aircraft, except that strategic bombing initiative belongs irretrievably to Allies. His logic is mathematical. Germany cannot match Allied bomber production, cannot develop equivalent heavy bomber quickly enough, cannot spare resources from fighter defense. Better to excel in defensive counter-air than fail at offensive strategic bombing. His arguments are strategically sound. They are politically unacceptable. Admitting German incapability in major warfare dimension contradicts propaganda, undermines morale, suggests eventual defeat. Major Baumann delivers this political reality to engineering team with unusual candor. The Führer demands we strike British cities in retaliation. He will not accept that we lack capability. You will design German heavy bomber incorporating Lancaster lessons. Whether it can actually be built in sufficient numbers to matter strategically is political question beyond your authority. Your task is technical. Provide the design. This directive clarifies their actual mission. Create propaganda of German capability rather than actual capability itself. The Lancaster taught them what excellence looks like. They must now create appearance of matching it regardless of practical implementation possibility. Dietrich realizes they have become participants in elaborate theater, designing aircraft that will never meaningfully challenge British bombing campaign, providing technical reassurance that resources exist for retaliation, maintaining fiction of German technological parity. The Lancaster study revealed truth. Germany lacks industrial capacity, organizational effectiveness, strategic commitment for effective heavy bomber force. But truth serves no institutional purpose when leadership demands comfortable fictions. January 1943. RAF Bomber Command's campaign intensifies. Operation Point Blank begins. Systematic targeting of German aircraft industry, ball bearing production, transportation networks. The strategic sophistication mirrors Lancaster's design philosophy. Comprehensive systems destruction, rather than isolated target attacks. The British do not merely drop bombs. They execute campaigns designed to create cascading industrial failures, using Lancaster's payload capacity and accuracy to strike specific industrial nodes repeatedly until destruction is complete. The German heavy bomber program, designated He-277 based on He-177 modifications, illustrates cascading resource constraints with painful clarity. February production schedule calls for 12 prototype aircraft. Actual output, 3 incomplete airframes. Why? Aluminum shortage because Allied bombing destroyed refineries. No replacement capacity exists. 4-engine configuration requires engines Germany doesn't produce in sufficient quantities. BMW 801 production committed to fighter needs. Jumo 213 still in development. Skilled labor shortage because experienced workers conscripted for Eastern Front. Replacements lack precision manufacturing skills. Transportation disruption because railway system bombed repeatedly. Components cannot reach assembly facilities. Ober-Engineer Dietrich reviews production reports with familiar despair. They are not merely losing ability to build heavy bombers. They are losing ability to maintain any complex aircraft production as industrial infrastructure collapses under sustained bombing. The Lancaster represents not just better aircraft, but better strategic system. Britain invested in bomber force capable of destroying enemy industrial capacity, successfully executes that mission, prevents Germany from building countermeasures through the very bombing those countermeasures would oppose. The strategic logic is circular and devastating. The Allied bombing strategy reveals planning sophistication Germany never achieved. Every raid coordinates with intelligence assessments, targets selected for maximum industrial disruption, follow-up raids scheduled before targets can recover. The Lancaster's payload capacity enables this, carrying sufficient bomb load to ensure target destruction in single raid, rather than requiring multiple attacks. German medium bombers lacked this capacity. They could damage targets but rarely destroyed them completely, requiring repeated missions that increased losses, while targets repaired between attacks. Captured RAF planning documents, obtained through intelligence channels, reveal British understood relationship between bomber capability and strategic effectiveness before war began. Pre-war plans envisioned heavy bomber force destroying enemy industrial capacity systematically. The doctrine was developed, the aircraft was designed, the production was organized, the operational methods were refined, all before the war made implementation urgent. Germany approached strategic bombing reactively, attempting to develop capability after war demonstrated its necessity. Reactive development cannot compete against deliberate preparation. The Lancaster succeeded because it was answered to question Britain asked correctly years earlier. March 1943. The Battle of the Ruhr begins. RAF Bomber Command's concentrated campaign against Germany's industrial heartland. Lancaster bombers deliver unprecedented tonnage nightly. German night fighter defenses improve. Better radar, effective tactics, experienced crews. Yet Lancaster losses remain sustainable. The bomber's structural resilience allows damaged aircraft to return home, crews to survive what would destroy lesser aircraft. Statistical analysis reveals sobering truth. Lancaster operational loss rate is 3.2% per sortie, sustainable indefinitely against German defenses. German bomber loss rates over Britain in 1940-41 averaged 4.8%, unsustainable, leading to campaign's eventual abandonment. The mathematics are brutal. RAF Bomber Command operates approximately 800 Lancasters by March 1943. Losing 3.2% per sortie while producing 300 monthly creates sustainable attrition. Germany operates approximately 300 medium-heavy bombers against Soviet Union, inadequate for strategic effect, unsustainable against improving Soviet defenses. The force structure disparity reflects years of different developmental priorities. Britain built strategic bombing capability systematically. Germany built tactical air force, attempted strategic bombing as afterthought, failed to achieve meaningful capability. Oberingenieur Dietrich analyzes this with intellectual clarity that provides no comfort. They studied the Lancaster comprehensively. They understand its design principles completely. They identified the secret of its effectiveness. Not single innovation, but systematic engineering for survivability, payload capacity, operational sustainability, redundant systems, damage-tolerant structure, crew efficiency, maintenance simplicity, dozens of design decisions accumulating into strategic effectiveness, and they cannot replicate it within German industrial organizational constraints. Hauptmann Werner articulates this in Memorandum to Reichsluftfahrtministerium. The Lancaster succeeds not through revolutionary technology, but through comprehensive excellence. Good solutions to every design challenge, integrated into coherent whole optimized for strategic bombing mission. We have identified these solutions individually. We cannot implement them collectively within current industrial circumstances. Building German Lancaster equivalent requires resources, time, industrial capacity we no longer possess. The opportunity to develop such capability existed in 1938. We chose different path. Tactical Air Force supporting ground operations. That choice now constrains our options irreversibly. The memorandum is classified immediately. Its fatalistic assessment contradicts official optimism. But privately, leadership understands the reality. Germany will not field Lancaster equivalent heavy bomber force during this war. The He-277 program continues because abandoning it publicly admits German inadequacy. Engineering teams design aircraft knowing it serves propaganda purposes more than operational requirements. They possess knowledge without power to implement it. Understanding arrived too late, revealed too much, demanded more than their industrial system could provide, under conditions of total war approaching its catastrophic conclusion. May 1943. Operation Chastise, the famous Dambusters raid, demonstrates Lancaster's unique capabilities. Modified Lancasters carry Barnes-Wallace's bouncing bombs, breach Möhne and Eder dams, flood Ruhr Valley. The raid's propaganda value exceeds its strategic impact, but it illustrates Lancaster's fundamental advantage: payload capacity and bomb bay design enabling weapons no other bomber could carry. Germany possesses neither aircraft capable of such mission nor organizational culture producing such innovation. Oberingenieur Dietrich watches newsreel footage of dam destruction with professional admiration and personal despair. The engineering behind the bouncing bomb is brilliant, solving seemingly impossible problem through creative physics application. The Lancaster made it possible. Only aircraft with sufficient bomb bay dimensions, payload capacity, stability for precise low-altitude delivery. German bombers could not have executed this mission with any conceivable weapon modification. The British identified strategic target, developed novel weapon, possessed aircraft capable of delivering it, executed operation successfully. Each element required years of preparation, institutional support, technical capability. Germany excels at individual elements but rarely integrates them into coherent strategic capability. Engineer Becker produces final comprehensive analysis of Lancaster structural design. The document details every aspect of the bomber's engineered resilience: geodetic-influenced construction, distributing loads efficiently, redundant control runs providing backup if primary systems damaged, self-sealing fuel tanks reducing fire risk, strategic component placement protecting critical systems from flak damage, crew positions offering protection while maintaining operational efficiency. Each design decision reflects operational experience, engineering sophistication, institutional learning. The report concludes, the Lancaster is indestructible not through armor or defensive armament, but through intelligent design anticipating battle damage and providing graceful degradation. British-designed bomber to survive missions, not merely to reach targets. We designed bombers to reach targets efficiently, accepting that battle damage would likely prove fatal. Both philosophies are internally logical. Operational results demonstrate theirs proves more effective for sustained strategic bombing campaign against heavy defenses. Our approach works adequately when opposition is light or missions are short. Their approach works adequately under all conditions encountered in strategic bombing. Dietrich realizes the Lancaster taught them about more than aircraft design. It revealed systematic difference in how Britain and Germany approached complex military problems. British think in terms of sustained campaigns, operational endurance, institutional learning, continuous improvement. Germans think in terms of decisive battles, initial effectiveness, technical superiority, revolutionary breakthroughs. Neither approach guarantees success, but strategic warfare favors the British approach, while tactical warfare favors the German approach. The war Germany is fighting has become increasingly strategic, and Germany optimized for the wrong warfare type. July 1943. Operation Gomorrah, the firebombing of Hamburg, kills 42,000 people in single week. Lancaster bombers deliver the majority of the tonnage creating the firestorm. The destruction exceeds anything previously experienced. German leadership demands retaliation, countermeasures, explanation for defensive failure. Oberengineer Dietrich has no satisfying answers. German night fighters are improving. Flak defenses are extensive. Radar coverage is comprehensive. Yet Lancaster streams penetrate nightly, deliver devastating payloads, sustain acceptable losses, maintain campaign indefinitely. The He-277 program produces 3 flyable prototypes by August. Test flights reveal aircraft with respectable performance, adequate speed, acceptable handling, reasonable payload capacity. Not Lancaster equivalent, but potentially useful. Then production reality intervenes. Full-scale manufacturing requires resources Germany cannot allocate: aluminum, engines, skilled labor, factory space, all committed to fighter production protecting against American daylight bombing campaign. The heavy bomber program is canceled officially in September. Prototypes are scrapped, design teams dissolved, facilities repurposed for fighter production. Hauptmann Werner observes the cancellation with grim satisfaction. His prediction about resource constraints proved correct, but correctness provides no comfort. Germany now completely lacks heavy bomber development program, while Allied bombers destroy German cities systematically. The strategic asymmetry is absolute. Allies bomb Germany freely, while Germany cannot meaningfully retaliate. This represents comprehensive defeat in strategic bombing dimension of warfare. Major Baumann delivers final assessment to engineering team in October. The Lancaster study provided valuable intelligence about enemy capability. It revealed British engineering sophistication we underestimated. It demonstrated organizational effectiveness we did not match. But it arrived too late for application. We learned what we should have understood in 1938. Strategic bombing requires dedicated capability, sustained development, industrial commitment. We made different choice then. Tactical Air Force supporting ground victories. That choice now determines our situation. Victims of strategic bombing without capability to respond equivalently. You fulfilled your mission perfectly. You understood the enemy's weapon completely. But understanding changes nothing when circumstances prevent action. This assessment crystallizes the Lancaster study's ultimate significance. Knowledge alone is insufficient. Understanding without implementation capacity is burden rather than advantage. The engineers at Rechlin learned exactly why the Lancaster succeeded, precisely how Britain achieved such capability, completely what design principles enabled its effectiveness. And every insight revealed how far Germany had fallen behind in strategic bombing development, how constrained current circumstances had become, how impossible matching British capability within remaining war timeline. They studied the weapon destroying their cities. They learned its secrets. They could do nothing with that knowledge except watch as strategic bombing continued unabated. December 1943. RAF Bomber Command operates 1E-100 Lancasters. The force continues growing despite combat losses. Nightly raids deliver 2,000–3,000 tons of bombs on German cities. The strategic bombing campaign has become industrial process. Targets selected systematically, raids executed routinely, damage assessed thoroughly, follow-up missions scheduled automatically. The Lancaster is instrument enabling this systematic destruction, its reliability and payload capacity making strategic bombing practically feasible rather than theoretically possible. Oberingenieur Dietrich, reassigned to fighter development after heavy bomber program cancellation, occasionally visits Rechlin to see the captured Lancaster. The aircraft sits in storage hangar, deteriorating slowly. Nobody studies it anymore. All lessons learned, all insights extracted, all knowledge documented. It has served its purpose as intelligence asset. Now it is merely artifact of war, memorial to German strategic failure in heavy bomber development. Standing beneath the Lancaster's wing, Dietrich reflects on what they learned and failed to learn. They understood the aircraft's technical excellence completely. Every structural innovation, every system optimization, every design decision. They identified the secret of its effectiveness, comprehensive engineering for survivability and payload capacity integrated into coherent design philosophy. But they missed deeper lesson until too late. Developing such capability requires institutional commitment, years before operational need becomes urgent. The Lancaster succeeded because Britain decided in 1930s that strategic bombing mattered, invested accordingly, maintained developmental focus despite competing priorities, built industrial capacity to sustain production. Germany made different choice. Tactical Air Force supporting blitzkrieg operations. That choice reflected strategic doctrine, available resources, institutional priorities in late 1930s. It was not obviously wrong when made, but it created path dependency, limiting future options. By time, strategic bombing's importance became undeniable. Germany lacked capability to develop competitive heavy bomber force quickly. Industrial capacity, technical expertise, production infrastructure, all committed to tactical aircraft. Pivoting to strategic bombers required resources not available, time not remaining, industrial capacity not existing. Engineer Becker, also reassigned to fighter work, joins Dietrich beneath the Lancaster. They stand in silence, two engineers contemplating civilization's failure encoded in enemy aircraft's existence. "We could have built this in 1938, Becker finally says. "We had the technical capability, industrial capacity, resource availability. We chose not to. Now we pay for that choice nightly as cities burn." Dietrich nods slowly. The Lancaster taught them that strategic choices have consequences that compound over years, that paths taken constrain future options, that capabilities not developed when possible become capabilities impossible later. Understanding arrived precisely when it could no longer matter. May 1945, Germany surrenders unconditionally. RAF Bomber Command's campaign ends after delivering 955,044 tons of bombs on German targets, approximately 70% from Lancaster bombers. The strategic bombing campaign destroyed German industrial capacity, killed hundreds of thousands of civilians, consumed massive defensive resources, and contributed significantly to Allied victory. The Lancaster was primary instrument of this destruction. British forces occupy Rechlin airfield days after surrender. Wing Commander James Morrison, RAF Technical Intelligence, leads team securing aviation research facilities. They find the captured Lancaster where Germans left it, partially disassembled, extensively documented, thoroughly analyzed. Morrison examines German technical reports with professional interest. The analysis was comprehensive, the understanding complete, the conclusions accurate. They identified every aspect of Lancaster's design excellence. German engineers, now prisoners awaiting processing, provide detailed briefings on their study. Oberingenieur Dietrich explains He-277 program with clinical precision. What they attempted, what they learned, why implementation failed. Wing Commander Morrison listens thoughtfully, recognizing kindred engineers speaking common technical language temporarily unburdened by war's hatred. You understood the Lancaster completely, Morrison observes, reviewing documentation. The structural analysis is excellent. The survivability assessment is accurate. Why did Germany not build equivalent capability? Dietrich considers his response carefully. We understood the aircraft. We did not understand soon enough what building such capability required. Sustained institutional commitment. Years of development. Industrial capacity deliberately created. Your Lancaster emerged from strategic decision made in 1930s to invest in heavy bomber force. Our strategic decisions led different direction. Tactical aviation supporting ground forces. Both choices were rational within their contexts. Yours proved strategically superior for total war. Ours proved strategically inadequate. We learned this from studying your bomber. We learned it too late for the knowledge to matter. Morrison nods slowly. This insight will appear in his intelligence report, not as criticism but as observation about strategic planning's long-term consequences. The Germans were not stupid or incompetent. They were trapped in strategic path dependency from choices made years earlier, when future requirements were unclear. Understanding this distinction matters for post-war planning, for preventing future conflicts, for recognizing that strategic decisions compound over time in ways not immediately apparent. The captured Lancaster will be flown back to Britain, reconditioned, possibly returned to service or preserved as historical artifact. The German engineers who studied it will be interrogated, their technical knowledge exploited, their insights into British capabilities documented thoroughly. Then they will be released to rebuild shattered Germany, carrying lessons learned at devastating cost. The bomber taught them about engineering excellence. The war taught them about strategic consequences. Decades later, historians would analyze Germany's Lancaster study as case study in technological intelligence's limitations. Understanding enemy capability does not automatically enable matching it. Knowledge and implementation diverge when strategic contexts differ fundamentally. The captured Lancaster became artifact of broader truth. Excellence in military capability requires more than technical understanding. It requires sustained institutional commitment, adequate industrial capacity, strategic foresight years before operational necessity emerges. The He-277 program gained footnote status in aviation history. Ambitious attempt to develop heavy bomber capability too late, with inadequate resources, under impossible constraints. This assessment is accurate but incomplete. It represented maximum effort German aviation industry could mount in 1943, and it proved insufficient for strategic requirements. Excellence within severe constraints remains constrained. The gap between adequate and truly effective determines outcomes when opponents possess superior resources systematically applied. Ober-engineer Hermann Dietrich survived the war, emigrated to United States in 1947, worked for Convair on bomber development programs. He never spoke publicly about Lancaster study. Private technical papers donated to Smithsonian Institution after his death in 1974 reveal engineer who understood that military capability emerges from strategic vision implemented over years, that reactive development cannot compete against deliberate preparation, that choices made in peacetime constrain wartime options more rigidly than most leaders acknowledge. The Lancaster itself became legend, symbol of RAF Bomber Command's effectiveness, icon of British strategic bombing doctrine, emblem of Allied victory through industrial might. The technical reality was more nuanced. Excellent aircraft optimally suited to strategic bombing mission, comprehensively designed for survivability and payload delivery, produced in quantities enabling sustained campaign. Not invulnerable, losses were significant but sufficiently effective and numerous to accomplish strategic objectives despite defensive opposition. The secret that made Lancaster indestructible was not single innovation, but comprehensive engineering philosophy, designing for battle damage survival, optimizing for crew efficiency during long missions, balancing payload capacity with operational range, accepting manufacturing complexity for strategic effectiveness. German engineers understood this completely after studying captured example, but understanding arrived when circumstances prevented implementation, resources exhausted, industrial capacity destroyed, strategic situation deteriorating beyond recovery. The true lesson transcended specific aircraft. Strategic capabilities require foresight, sustained investment, institutional commitment over years. Reactive development provides inadequate response to threats emerging from opponents' deliberate preparation. The side that anticipates future requirements correctly and invests accordingly holds decisive advantage over opponent attempting to match capability after operational necessity becomes apparent. Germany learned from Lancaster. Britain had already implemented the lessons. Victory came to side that asked correct strategic questions years before war forced answers to become urgently necessary.